We now move on to the underdetermined problem. In the underdetermined problem, ax equals b, there's actually an x that makes this happen. In fact, there's at least one solution. We'll call that solution x naught. That is a solution to this equation. There are likely an infinite number of solutions. So in the underdetermined case, there's at least one solution. And because of the fact that ax is equal to b for some x, minimizing the norm of ax minus b is not meaningful because there's at least one x that will give you 0. Okay? And it's possible that there may be an infinite number that give you 0. So which one do you choose among all those? And so instead of using that problem, we actually change the problem so that we find the smallest of all the solutions. So that is, we actually change it to this problem. Again, we have a constrained optimization problem. We're going to minimize the norm of x squared subject to ax minus b is equal to 0. That is, the only x's that we consider in this minimization problem are the x's that satisfy this equation. Okay, so those are the only x's we consider. So note that if both x and x star are solutions to this equation, then if I take delta is equal to x star minus x, then a times delta is equal to a times x star minus a times x. But since these are both solutions, then ax star is equal to b, ax is equal to b, we get b minus b is 0. So what does this say? A times delta is equal to 0. That is, delta is in the null space of A. Okay, so the difference in solutions between two solutions lies in the kernel of A. So we again compare solutions. X star plus delta norm squared minus x star squared. We can go through and show that's equal to delta squared plus 2 times the inner product of delta with x star. So notice that we have this cross term, the inner product of delta with x, and so as before, the cross terms determine whether x star is a solution or not. Okay, and so that leads us to the theorem that proves or that establishes the solution, the point solution for the underdetermined case. So the vector x star is a solution to this problem, norm of x squared minimized, subject to ax minus b is equal to 0, if and only if ax star is equal to b and x star is in the range of A adjoint. Wow, that's unusual. This is kind of an unusual looking condition. Okay, well obviously ax star must be equal to b, or it can't even enter the election for the minimizer. Okay, but for x star to be in the range of A adjoint, that's something different. All right, so, but again, this is shown and proved in the video on proofs. So you can go look there and see the video on the proof of this. But this establishes the point solution for the underdetermined case. We can also look at the solution map for the underdetermined case. The matrix B is a solution map if and only if this normal equation, notice that this normal equation is different than what we had before. Here the A adjoint is on this side, the B and the A are multiplied in the opposite order, so we have a different normal equation in this case. Okay, so this is, again, we go through and prove this kind of thing. So notice that here we have something like a normal equation that pops out. This is actually a normal equation. All of this actually is equivalent to this normal equation, and you can see that in the proofs, but it's not obvious here. So in looking at the case, the underdetermined case, where you may have an infinite number of solutions, okay, we use something called the orthogonal complement of a matrix. So we talked previously about the orthogonal complement of a subspace. You have a subspace and you have its orthogonal complement. Well, if we think now of our subspace being the kernel of A, and let B be a basis for that kernel. That is, B is a set of vectors linearly independent that span the kernel of A, the null space of A. We now form from these basis vectors the matrix A perp, and so we have that A times A perp is equal to 0. That is this matrix that we form from the basis of the, so that is every column in here multiplying by A gives 0. Okay, so we have this. If x naught then is any solution, then if I take x naught plus A perp times V, this is also a solution for any vector V. And so we can actually find a parameterization of all solutions of the linear algebra equation, and they're all of this form. Okay, they're a solution plus this a orthogonal complement times any vector. So you can go through and show that if I take this now, vector, multiply on the left by A times x naught is B, A times A perp is 0, and so we get A times this is equal to B, a solution. So now we have seen the solution to the underdetermined problem.